Let's talk about Boolean algebra and how to use axioms and theorems to simplify Boolean equations. So similar to regular algebra, we can use axioms and theorems to manipulate the equation and make it simpler. So simpler means fewer terms. And it's like regular algebra, but it's actually simpler because the variables only have two values, 1 or 0. And there's this property of duality in these axioms and theorems where ands and ors and zeros and ones can be interchanged, and the axiom or theorem is still true. So here are the Boolean axioms. Axiom 1, this numbering is arbitrary, but these axioms are axiom 1, b is 0 if it's not equal to 1. So this is defining the binary field. So basically what the variables are that we're dealing with. They're either 1 or 0 if it's 0 if it's not 1. And the inverse of 0 is 1, so this is defining the not function. And now we're going to define, so far we're just defining the and function, where 0 and 0 is 0, 1 and 1 is 1, and either 0 and 1 is 0, and also 1 and 1 is 0. So this is defining how the and function operates. And then we can introduce the dual form where we replace our ands with ors and our zeros with ones and ones with zeros, right? So we replace our and ors with ors with ands, zeros with ones, ones with zeros, and we get the dual form of the axiom. So the first one, the binary field, well, b equals 0 if it's not equal to 1. Replace that 0 with a 1. B is 1. That 1 with a 0 if it's not equal to 0. So now we have the entire binary field. The inverse of 0 is 1. The inverse of 1 is 0. Now we've defined the not function, or the inverse function, and by replacing ands with ors and zeros with ones, we now define the or function in its dual. 1 or 1 is 0 is 1, 0 or 0 is 0, and either 1 or 0 or 0 or 1 is 1. Now we can define our theorems of one variable. So we have the identity theorem. B and 1 is B. So if we put B into an and relationship with 1, we're going to get back itself. So that's identity. B and 0 is 0. Well, this anding with 0 nulls out the effect of anything it's anded with. B and B is B, so idempotency. I can and B as many times as I want. B and B and B and B. That's still equivalent to just B. And involution, if we invert something twice, we're going to get back just the variable. And if we and a variable and its complement, we're going to get 0. Why? Well, because one of those terms is going to be 0 no matter what, right? So if B is 0, well, there we go. 0 and anything is 0. Or if B is 1, well, then B bar is 0. And we get 1 and 0 is 0. So no matter what, when we and complements together, then we're going to get 0. And again, these theorem numbers are arbitrary, but these names are not. And so we can do the dual form where we replace ands with ors, zeros with ones, and we get, right, replace this and with this or, 1 with a 0, and we get the dual form of identity. B or 0 is equal to B. And we can see why we use, here's an example of why we use the and, or the multiplication symbol for and, because B times 1, if we were just interpreting it as regular algebra, is also equal to B. B plus 0 is also equal to B. So we are using or, but this is one of the reasons we've overloaded those specific symbols, because they have similar properties in many cases. Not all, but many. And so we get B or 0 is equal to B. If we put B in a relationship, or a variable in a relationship with an OR relationship with 0, we're going to get back that variable. B or 1 is equal to 1. Well, if we have anything in an OR relationship with 1, the OR 1 nulls out the effect of anything else. And so it's called the null element. It nulls out the effect and we just get 1. Idempotency, B or B or B or B or B. Right, that's what, like repeating something 20 times, clean your room, clean your room, clean your room. Well, it's the same as saying it just once, and usually has about the same effect. Okay, so involution, there's no dual form of that. Complements. Now, if we OR two complements together, B or B bar, we're going to get 1 because one of those terms is 1 no matter what. Either B is 1 and we get 1 or something, turns out 1 or 0, but anything in an OR relationship with 1 is 1. Or if B is 0, then B bar is 1. We still have the OR 1 relationship and we get 1. So in an OR relationship, when we OR complements together, we get a 1, but when we AND them together, we get a 0. People often, kind of flip those, so don't do that. So here's some, graphically we can look at these theorems. The identity theorem, B and 1 is B. Well, B and 1 is just like a wire, right? Anything ANDed with 1, that's AND 1 says, yep, go ahead and go through, right? So B and 1 is just equivalent to just a wire. And so we can see why using these identity theorems, we can get rid of a gate in our circuit by reducing it to just a simpler form. B or 0 is just equal to B. If we have an OR gate with a 0 in it, that 0 doesn't do anything. It's not going to make this output 1. It depends on what B is to make that output B1. B and 0 is 0. B or 1 is just 1. Anything ORed with a 1 already has a 1 on that OR gate. So we're going to get a 1 on that output no matter what. B and 0, well, there's no way to make the output of this AND gate 1 because we have this and 0. We have this, one of our inputs is tied to 0. So it's equivalent to just a wire tied to 0. Idempotency theorem, B and B is just the same as a wire tied to B, B or B, wire tied to B. Identity theorem, B bar bar equals B. So if we invert something twice, right, B bar, we're going to get the inverse of B, then we invert it again. We're going to get B bar bar, which is the same as B. So for example, if B is 0, invert it once, we get 1, invert 1, and get our B back. If it were 1, we invert it once, we get 0, invert it again, we get our 1 back, right? So B bar bar is just the same as B. B and B bar is 0 because one of those inputs is going to be 0 no matter what. B or B bar, if we OR complements together, we get a 1 because one of those inputs in that OR gate to that OR gate is 1 no matter what. So here are our basic Boolean theorems. And these are theorems of one variable: identity, null element, idempotency, involution, and complements.